Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over again finding equilibrium concentrations, but this time what happens, how do you do that if all you're given is the equilibrium constant and the equilibrium concentrations. You're not given anything, not the equilibrium, but the initial concentrations. You're not given any equilibrium concentrations or anything else. So how would you figure it out this way? In this sort of problem where all you're given is the equilibrium constant as well as the initial concentrations. How do you solve that problem? In that type of problem, you're going to have to use what is called an ICE chart. So I have it written here, and I stands for initial conditions, initial concentrations, the concentrations you begin with. C is for change. That's the change that is undergone, that is underwent by the reactions and the reactants and products. And the equilibrium is the concentration that is gotten at equilibrium. So the concentrations of your reactants and products at equilibrium. And so when you're doing your ICE chart, since all you're given is the initial concentrations and your equilibrium constant, you're going to have to use some algebra, and you're going to have to use x as the amount of change. Okay, so I'm going to go through a couple of examples and show you how it's done. So the first thing you need to do is you need to take the initial conditions and you need to do a Q, your quotient ratio, your reactant quotient. Sorry. And the reason for that is because you need to figure out whether it's going to go to the left or the right. Is it going to go towards products or is it going to go towards reactants? Now, in the examples I'm doing, it's pretty obvious which way it's going to go because we have no product here. So if all I have is reactant and no product, obviously it's going to have to go in the direction to make some product, right? So, but you should be in the habit of doing a reactant quotient before you start your problem, because you could be given a situation where you have all these initial conditions, all the initial concentrations are non-zero. So I could have a concentration of reactant already. I don't know if it's at equilibrium or not, right? So you always do you always do your quotient, reaction quotient, to see whether or not you are at equilibrium, and if so, or if not, which direction are you going to go? So you need to figure that out, because if you don't figure that out, you don't know if the change is going to be minus on your reactant side, or if it's going to be plus on your reactant side, or minus or plus on the product side. So you need to do that first. So you set up your Q value, right? So Q, and that's going to be defined just like your reaction, your equilibrium constant. So if we set that up, it's going to be NO, the concentration of NO squared, over these two concentrations. So concentration of N2 multiplied by the concentration of O2. And if we put those in, we plug in these values. So this is going to be 0 over 0.2 times 0.2, 0.200 multiplied by 0.200. Obviously, that's going to be 0. Once you get your reaction quotient, you're going to compare that to your I'm blanking on the equilibrium constant. So you're going to compare these two, and depending on whether or not Q is less than, equal to, or greater than your equilibrium constant, that's going to determine whether it's going to go to the right or to the left. If Q is less than K, that means you have more reactants and less product than you would have at equilibrium, so you need to make more product. So you're going to go in towards the product. So obviously 0 is less than 0.1, so we're going to go in the direction of making product. if Q was greater than the equilibrium constant, then we would go towards reactant. So now that we know which direction we're going to be going this way. So whatever the change is over here is going to be negative, and the change over here is going to be positive. And we're going to represent that change by the value of x, or we're going to represent it by x, the variable x, or the letter x. So now what we're going to do is we're going to look at our equation, and we're going to look at the balanced equation and the mole ratio of the substances with respect to each other using their coefficients. So that's going to tell us how much change is going to be involved stoichiometrically. So if we look at x here, or we look at the change that's going to go here, so there's going to be a certain amount lost by the nitrogen. We don't know what that amount is. We're going to represent that as x. So we say x is the amount of change, the amount of loss. And we're going to say minus x because it's lost. We're losing reactant. So we're going to lose reactant, form product. So whatever amount of that reactant we're losing, we're going to represent that as x. Since both nitrogen and oxygen both have a coefficient of 1, they're both going to be x. So this is also going to lose an x amount, okay? And again, that's because the ratio is 1 to 1, so it's x to x. Now for NO here, NO is going to be gain. We're going to form product. So the amount here added is going to be added instead of lost. And so, again, looking at the mole ratio here, for every amount lost here, we're going to gain double here. So we're going to lose here, we're going to gain here, but it's going to be double because it's 1 to 2. So the amount here is not going to be x, but 2x. So we're losing x amount here, we're losing an x amount here, and we're gaining 2x amount there. So that's how we set up our change. Okay, so once we have our change, the amount at equilibrium is going to be these two, the I and the C added together. So the amount at equilibrium here is going to be 0.200 minus x. And the same thing here, it's going to be 0, I have 0.200, and then minus x. And then for here, it's going to be 0.00 plus 2x, or just 2x. And so now I have my equilibrium amounts. So now that I have my equilibrium amounts in terms of x, now all I need to do is solve for x. And the way I'm going to do that is I'm going to take these equilibrium amounts and plug them into the expression for my equilibrium constant. And so we're going to have our expression for Kc going to be the same expression, but this time it's Kc. So it's going to be concentration of NO squared over the concentrations of N2 times concentration of O2. Okay, so then all we need to do is then take everything and plug it into our expression. So that means we're going to have, for the Kc, it's 0.10 is equal to, and then for these three, we're going to plug in the equilibrium concentrations with x. So this is just 2x, so it's going to be 2x squared over, and then these two are exactly the same. They're going to be N2 times into. So this would be this times this, which is this squared. So I'll just skip that step, and so I get 0.200 minus x squared. And that's because I am plugging these in. So 0.200 minus x for here times 0.200 minus x for here. Those together multiplied is the same as 0.200 minus x squared. Okay, so I have it set up. Now all I need to do is solve for x. And for this one, it's going to be simple algebra. Sometimes you're going to have to use the quadratic formula. That'll be in the next problem I'll show you that. But sometimes you don't. In this one, it turns out we don't have to, because I can get rid of the square by square rooting both sides. So I can take the square root of both sides, and I can get rid of the square, and then at that point it's just algebra. So at that I take the square root of, well, what's the square root? Let me double check. Okay, so I'll do it later. So then what we do is we take the square root, so it's going to be the square root of 0.10 is going to be equal to, and then I have 2x over 0.200 minus x. Now I multiply both sides by 0.200 minus x. Right, so then this becomes 0.200 minus x. So I got these two multiplied. So this is going to cross out. So now I have 2x is equal to this times this. Okay. So then all I need to do is multiply these two, multiply this through this. So then I'm going to bring this down here. I'm going to use this space here. So then this becomes 0.200 times the square root of 0.10, and that's going to be minus the square root of 0.10x is equal to 2x. And so I have that there. So now I can bring x over here, so I can then bring that over here. I can multiply this, and then when you solve for x, you get 0.027. So here x becomes 0. Let me look at that again. 0.027. Okay, so that's the change. That's my x value for what I found. So now that I have the x value, now that I can go in and plug in this value for the x's here to find the equilibrium concentrations. And so right away, so the 0.200 minus x minus 0.027, that becomes 0.173. So this is going to be 0.173 molar. And these are the same, so this is also going to be 0.173 molar. And then this one is going to be 2 times x. And this is going to be 0. So this will be 0.054, I believe. 54. And that's how you find the equilibrium concentrations when you're only given the initial concentrations and your equilibrium constant. I hope this was helpful. If you like this video, please like, share, subscribe, hit the notification bell. Thanks for joining me. I'll see you next time.